Physics, Chapter 3, Section 2. And this screencast goes out to Alexa, who apparently is sitting around on a Saturday night at 8 o'clock at night when all her friends are out partying, contacting her physics instructor saying, "You forgot to give us homework." So here we go. Here's your homework. So we're going to look at this idea of constant acceleration, and we're going to pay particular attention to the graphs. Essential questions. Feel free to read. If you need to pause to look at this, you could do so. We want to look at this idea of displacement. Remember, displacement is not exactly the same thing as position. It's basically the change in the position, in other words, is equal to the final position minus the initial position. But displacement has both magnitude, usually measured in meters, and some kind of direction. Okay, so let's take a look at this idea of positive acceleration or constant acceleration. Here we have position versus time, and as we can see, as the time goes on from 1 second to the next, we're seeing a position change. We notice that between the first second up to the first second is only changed by 2.5 meters. The second it changes by a total of 7.5 seconds to get it up to 10, which is quite a bit. The third second, it's changing by 12 seconds. So we could see that 2.5 seconds, 7 seconds, 12 seconds, about 18 seconds. In other words, it's getting larger and larger as we're going on. Obviously, we're having some kind of acceleration going on here. If we were to graph these various, the position at various different times, what we would see is a parabola. And if we looked at the tangent to the curve at different points, we would see the slope of the line, and we would see the slope of this line is getting steeper and steeper. If we graph this, so we have an object, constant acceleration, the position, this is a position time graph and this is a parabola. Now if we graph it, something kind of cool happens. We end up with a straight line. I think it's cool anyway. The slope from the position versus time graph can be used to create a velocity versus time graph. And the slope shows shown in the position time graph are the same as the velocities in the graph. So basically we can graph this out, and now we have a velocity versus time graph. And we get a nice straight line. This slope is equal to the acceleration. So keep that in mind. We're going to see this time and time again. All right. So can we find a unique position time graph? Nope, not from this velocity graph, because we don't have any information containing the object's position. We're going to have to find that from the context of the question. However, the velocity versus a time graph does give us, it tells us displacement. It tells us how far it's moved. Recall that an object's moving at constant velocity, so if we want a constant velocity, it's basically change in x over change in t. Change in position over change in time. If we graph that out on a velocity graph, here we have a constant velocity, in other words, zero acceleration. It's at 8 meters now, it's at 8 meters here, there, and so on and so forth. It's always at 8 meters per second. So if it's at 8 meters per second, we can then figure out how far it travels between the first second and the third second. We have a change of 2 seconds at 8 meters per second. It's going to be 16 meters that it changes. Okay, so that's if we have a constant velocity. But what happens if we have a changing velocity because due to acceleration? We're going to define acceleration is the change in velocity over change in time. We're also going to manipulate this equation around a little bit to get the change in velocity is equal to the acceleration times time. Change in velocity is basically the final velocity minus the initial velocity is equal to acceleration times time. This is about the only new equation that you're going to get during this time. There's going to be a bunch of other equations, but we're not going to focus on them. The equation for final velocity with an average acceleration then can be written this way. The final velocity is equal to the initial velocity plus the product of the average acceleration and the time interval. Looking at this in cases, so again looking at this equation, in cases in which the acceleration is constant, the average acceleration is the same as the instantaneous acceleration. In other words, whatever they're the same thing. They're the same number. The equation for the final velocity can be rewritten to find the time if we needed to get the time. In other words, if I give you the acceleration and I give you the velocity, you could figure out the change in velocity. You could figure out what the how long the time is. So we could figure out if we have these various different points. There's 4 different things here. If I give you 3 out of the 4, you could figure out the 4th. That's all this is saying. All right. So once again, we have a constant velocity of 75 meters per second. We have time written across here in seconds. And so it says find the displacement of the airplane at t equals 1 second and t equals 2 seconds. We'll look at the area here. The area under this curve for 1 second would be 1 base times height. 75 times 1 is 75. For 2 seconds, again, 75 meters per second. And so the base is 2, the height is 75, base times height, 2 times 75 is 150. Okay, we go through all the analysis. I'll let you guys read through this if you want. You could pause and read this stuff. This is basically just showing you all the knowns and the unknowns, and then how to solve it. We're going to use an equation here, and we substitute in our values for the equation. For the first velocity, the velocity is always 75, so for the first time interval is 1 second, we just substitute in, we get 75. Second time interval is 2 seconds, substitute that in, and we get 150. And we want to make sure that our displacement should end up in meters, and if we have meters per second times seconds, the seconds cancel, leaving us with meters, so we're good. Do the signs make sense? The positive sign does agree with the graph, and moving a distance of about 1 football field in 2 seconds is reasonable, so that's fine. Alright, so now let's take a look at another one. Oh, this is just saying the steps that we covered. Again, I'll let you read that if you really want to. And we evaluated our answer. Now, here's where it gets fun. What happens if we don't have a constant velocity? We have an initial velocity down here. We have a final velocity someplace up here. We now are going to end up with a triangular shape. If the acceleration is constant, this is going to be a straight line, and now we get a triangle. Just like before, if we had a constant velocity and we had time, we would just multiply base times height. However, we got a triangle in here now. So what we're going to do is we're going to add the area of the rectangle to the area of a triangle. And what's the equation for the area of a triangle? 1/2 the base times the height. So these are not new equations. You'll learn these in geometry. We're just going to start applying them. So once again, we have our velocity graph in meters per second, time across the bottom. And the equation looks like this. Delta x, or change in x. We need the change in x for the rectangle, change in x triangle. We add them together. The initial velocity times the time, that's this down here, gives us the area of the rectangle. 1/2 the change in velocity is essentially the height. Change in time across the bottom is the base, so we have 1/2 height times base, or base times height. Now, let's go ahead and figure in acceleration. We said that acceleration is change in velocity over change in time. So if we manipulate the equation, we have velocity is change in velocity is acceleration times time. which means now we could substitute into the equation for change in velocity here. We could substitute in acceleration times time. Well, I probably could have had another step in here where I had velocity, acceleration times time times the initial time. So now I have acceleration times time squared. So now we're starting to get this equation. If we graph it, again, this stays the same, but up here we now have 1/2 the acceleration times the time. So we're getting this equation in here. Another transformation is, if you recall, delta x is equal to the final velocity, final position, final displacement minus the initial displacement. So if we put that into the equation is equal to all this stuff, we can then rewrite it by adding x initial to both sides, and now we have x final is equal to x initial plus velocity initial times the time plus 1/2 the acceleration times the time squared. Is all that fun? Yep. But here's the good news. You don't have to do all that stuff, because I'm going to give you an equation, and we have 1/2 the base times the height plus base times height. That's going to give you displacement. That's all you need. You don't need all of this stuff down here. If you can remember how to do the area of a triangle, 1/2 base times height, and the area of a rectangle, base times height, that's all you need. These are those previous slides without all my pictures that I put in there. And so this is just saying that if we start with an initial time of 0, instead of saying change in time, we could just say time final. And that's all we did with that equation. And before I get you back to the easy way of doing things, we're going to show you one more manipulation that you're going to see in the book, and that tells you that if you don't have the time, but you want to work with just the velocity, the acceleration, and the displacement, there is an equation that will do that for you as well. But for this class, you're just going to use, you're going to diagram the graph, and then you're going to do 1/2 base times height for any triangle, base times height for the rectangle. The last thing you need to know is how to do the slope. Real easy. Rise over run. So if you know rise over run, which you learned as a sophomore, and you learn the area of a triangle, which you learned as a sophomore, and you base times height, which you learned as a sophomore, you have everything you need to do physics. Okay? And you don't need all those equations. If you want to do the equations, come in during Open Lab and we could labor through the equations. Otherwise, this is the way we're going to solve the problems. So what would that look like? Okay, so let's take a look at a problem. It says a golf ball rolls up a hill of a miniature golf hole. Assume that the direction towards the hole is positive. If the golf ball starts at a speed of 2 meters per second, slows at a constant rate of 0.5 meters per second squared, what is the velocity after 2 seconds? Okay, I drew a little graph down here. You don't even need to use graph paper for this. Okay, because what do we know? Well, we know we started at 2 meters per second. So put a dot on 2 meters per second. We know we're slowing down. That means that we're going to have a slope. And the slope is going to be negative if we slow down, positive if we speed up. We know we want to figure out for 2 seconds. So what are we trying to figure out here? Well, you have a triangle. And so if we want to figure out what the velocity is after 2 seconds, we know that it's going to slow down. Okay, and we have a triangle here, and we know that the slope of this triangle, we're told, is 0.5 meters per second. So we know that the slope 0.5 is equal to rise. That's going to be that's what we're looking for over here, is the rise over run. And what's the run? We're told the run is 2 seconds. So we have So we got rise over run after 2 seconds. We started at 2, and we're going to decrease it by a certain amount. How much are we going to decrease it by? Well, multiply 2 times 5 and you get 1. It's going to decrease by 1 second. Now it says what's the velocity if the constant acceleration continues for 6 seconds? Well, substitute in a we're going to substitute 6 seconds in there, and now we have a decrease in by 3 seconds. 6 times 0.5 is 3 seconds. Well, we only started at 2, so what does that mean? Well, that means that our slope actually, see if I can get it to pick up the slope, actually ends up at, after 6 seconds of going past the 0, and ends up being a negative 1 meter per second. In other words, it's rolling back down the hill. That's all it's saying. You didn't get it in a hole. It's rolling back towards you. So describe the motion of the ball in words. It starts out positive. It slows down, slows down, slows down, comes to a stop, starts rolling back at you, and it's rolling towards you after 6 seconds at a negative 2 meters per second. All done without any of those fancy equations. Let's take a look at another one. Here we have interpreting some graphics. The first one, if we want to interpret this up here, it says it has 2 bicyclists, and it says we start from rest and travel north, increasing their speed at a constant velocity. What is the total displacement of each bicycle? Right, we're looking for the area of the triangle. So the blue triangle, 1/2 base times height. Base times height, 3 times 6 is 18. Half of that is 9. Answer, we already got our answer. Okay, and then for the red triangle, once again, half the base times height. So the height is 4, the base is 4. 4 times 4 is 16. Half of that is 8. So we have our answers without using all those equations. In the second graph here, it says the motion of 2 people, Carlos and Diane, are moving along a straight line described in the graph. What is the total displacement of each person at 4 seconds? So we're looking at 4 seconds. So let's look at Carlos. Carlos, here's his triangle, his shape, rectangle. I figure out the rectangle, base times height. 2 times 4 is 8. Diane, on the other hand, triangle, how to figure out triangle? Half base times height. 2 times 4 is 8. Half of that is 4. So she's only traveled 4 meters. He's traveled 8 meters. After 4 seconds, they're not at the same spot. This is a velocity diagram. It tells that they're traveling at the same velocity. Now, if you want to figure out when will they be at the same spot, well, now you need to figure out when Diane's triangle is going to be equal to Carlos's rectangle. And we can figure that out. The time is the same for both of these, but we would have 2 equations with the time being the same. We're going to leave that for later on, though. Finally, we have a car is accelerating at a constant rate from 15 meters per second to 25 meters per second while traveling 125 meters. How long does it take to achieve final speed? So we're looking for a time equation. So let's go ahead, move this up. Got to draw our and we're starting at 15. So we need 15 on here. And we're going to 25. Come on. And we're looking for time. And we know we're speeding up, so we're going to draw a line speeding up. Okay. So what do we have here? Well, we have a rectangle. And we have a triangle. We know what the change in velocity is. 15 to 25 is 10. So we have a delta V here. And we have a initial velocity of 15. The thing we don't have is the time. But what we do have is we have the distance. These two together would add up to 125. And that's going to equal the base one. The rectangle is 15t plus, and then the other one is going to be 1/2 the base, which is t. Well, let's go ahead and put in the, so 1/2 of 10 times t, 1/2 the height times the base. I'm switching those around just because that's the way they do it. What's 1/2 of 10? 5. So 15t plus 5t equals 125. 15t plus 5t equals 20t. Divide both sides by 20. And we're getting t is equal to 125 divided by 20, 6.25 seconds. Unless you want to go find an equation that has an initial velocity and a final velocity and a delta x, and you don't know what the acceleration is, and you're trying to solve for t and all that kind of stuff, or you could do my diagrams. Your choice. Come in during an open lab and I'll show you how to do all this using the fancy physics equations, or you could simply live with what I'm doing here. Anyways, that's about it.